Honors Algebra 2. Yesterday we looked at 2-4, writing equations of lines. We're going to continue that concept in 2-6. We talk about line of best fit. So for this one, we're going to be able to create a scatter plot from data. And then we're going to take that scatter plot and can fit a line to that scatter plot. And then we're going to look at correlation. How does our line best describe, or how does it fit the data? And then we're hoping to extrapolate the data a little bit using our line of best fit. So linear models just takes data from life, and then we put it in some kind of line plot, a scatter plot, and we look for trends. And so for this one, obviously, this is the hourly minimum wage since 1938 to 1997. And kind of looks at some of the changes that occurred in those years. And as you look at this, you can see how it just over time has increased. Now, is this a line? No, but is there a linear relationship? It appears that there is a linear relationship. So we can write linear equations that model real-world data. So the whole theory about 2-6 is that we can take some kind of data, and then we can draw some line to model that data, and then we can use that line to then predict what will happen in the future, and then we can actually change that a little bit as the years go on, what happens to the next few years. Another example, in word problems, they will give us data, or in application problems, we can give in data that we can still write equations from. And this is really just 2-4's information, where they give us some information. We're given an elevation of 12 feet, and then we're rising 50 feet per minute. So we want to write the equation for that. So this one is y equals 50x plus 12, because 50 feet per minute is a rate, like a slope, and then 12 feet is a starting value. And then it says graph the equation, interpret the intercept at which the graph intersects the vertical axis. Well, this would be the y-intercept at 12 feet at time 0. That's how far you are above sea level. And then 50 feet is just the speed at which you increase. So suppose the balloon begins descending at a rate 20 feet per minute from an elevation of 1350, so we can model this as well. So decreasing at a rate of 20, so we're going to take our slope, negative 20, and that's the only one that's a slope of negative 20, and it has a starting value of 1350. So example 2 we have, this is similar to yesterday. We're given a word problem, and then inside here we should see that we're given 6 inches of the candle, and then it's after 1 hour, and then after 3 hours it's 5 1/2 inches. So we're given some data to help us find the rate at which it is decreasing. And so here's your 2 points. From these 2 points, we can go through the same steps as yesterday. We can find the slope. So if I do that, we can take the 6 minus the 5 1/2 over 1 minus 3. So then we have a half divided by negative 2, which is the same as multiplying by negative 1/2. So negative 1/4. So this would be the rate, or the slope of the candle decreasing. So looks like a negative 1/4 inch or a 1/4 inch decrease every hour. You can write it like that if you wanted to. Then point slope form to write the equation. So here's point slope form: y minus y1 equals m times x minus x1. So we plug in our y value. So, and it doesn't matter which point we choose. I'm guessing that most of you want to use this point to have whole numbers to start with. So let's plug in 6. Our slope is negative 1/4. And x minus 1. So we have y minus 6. Distribute the negative 1/4. And add 6 to both sides. Here's how that basic math fraction work. You gotta do this really quick. Add 6, so it's just plus 6 1/4. So there's the equation to describe this situation, and we can use that in the next part. So we can use this equation from example 2. When will the candle be 4 inches tall? So we're trying to find its height. And so back in the equation we have our x value and our y value. Our x value is our time in hours, and y is our height. So we actually are trying to figure out when is our height 4 inches. And so we can plug that into our equation, and then we can try solving for our x value, our time. So we subtract the 6 1/4, we have negative 2 1/4 equals negative 1/4 x. And then we could multiply by the reciprocal. I'm also going to change this into an improper fraction, so that's the same thing as negative 9/4. And then let's multiply by the reciprocal. So we're multiplying by a negative 4 to both sides, which is nice because those reduce out, so we'll have 9 is x. So this is in 9 hours, the candle will be 4 inches tall. So given a scatter plot, we should be able to find equations that represent the scatter plot. Now they won't be exact line going through all points, but the equation can represent the points, a line of best fit, or a model. And so the model is just the equation. So in here, when we're trying to write the best model for this, we're looking at the positive slopes, we're increasing. So right away I can get rid of the negative slope one. So right now we're down to 4x and 6x, which they both seem plausible. But then we look at the y-intercept. One's at 4 and one's at 30. Well, 30 is way up here. And obviously 30 is not going to be a good y-intercept. So it has to be D. Y-intercept of 4, and then an increase of 6 over 1. So seems good. A scatter plot is just a plot of the points relating two different sets of data, and then we can take a scatter plot and apply some kind of correlation to it. How does it look? And so there's some different kinds. We have a moderate positive correlation, strong positive correlation, a moderate negative correlation, strong negative correlation, and no correlation. And the correlation actually has a value, correlation coefficient, which we use R to note that. If R is equal to a positive or negative 1, it is a line. The closer it is to positive negative 1, the more linear the relationship is between the x and y values are. The closer it is to 0, the less it is to a line, or less of a linear relationship it would be. So if we're trying to use a line to describe it, R values that are close to 1 is what we're looking for. And so when we're looking at this value here, these points, this scatter plot, we can say it's a positive moderate, positive strong, positive negative, strong negative, or no correlation, and it should be pretty obvious. There's not much correlation here, meaning as we look at the graph left to right, are the points generally going up together or downward together? This one here, they're going down. As we look left to right, they're going downward. So it tells me it's going to be a negative. This is going to be a moderate negative, when this one here is going to be a strong negative. Strong negative because the points are closer together. And then D here, this will be a moderate positive. They're increasing, but not really tight. And then E here would be a strong positive. And so if you're looking at R values, we'll have a calculator tomorrow find the R values for us, the correlation coefficient. But we should have an understanding of the way the points are, how strong the correlation would be, or what is a strong, what is a moderate kind of correlation. Things in life that have a moderate correlation still have value. So when you start having correlations that are greater than 0.6, they have value in statistics. Values that are much higher, like this one here, the strong correlation, you're talking in the 0.9 range or above. So that's a very strong correlation. So last slide here, example, just where we're given the years that you were born, and then the life expectancy for males, females, and in total. So we can just take that data, we can make a table of that, so an XY chart of the life expectancy at birth, given the year you're born. We can create a scatter plot for that, we can create a line. Now when you do that, when you create your line here, your line that you're drawing does not have to go through any points. Now this one happens to go through this point here. Looks like it might hit this point here. And maybe not any of these. But if it doesn't have to go through any point. You just want to find a line that best represents the points. When I'm drawing my line of best fit, I'm doing my hand, I tend to try to find some nice pretty points. So if it was me, I would probably choose maybe this point here, and then maybe this point here, or this point here. Either one would probably be good. Might actually. So if I was choosing it, I would choose maybe this point here, probably a better choice than here. And then I would draw the line going through those 2 points. And then that's a pretty good approximation. Now, the whole point about talking about the points is why do I care about which 2 points to choose? Is I'm going to choose nice and easy points for me. So I actually choose the points before I draw a line. Now I have these points, 454, and then the point 8874. Now I have 2 whole number or integer points, and it's pretty easy to graph, or pretty easy to find the equation of. And so that's why I have some thought process before you just start throwing down a line. Find some points that represent the other points, but make it easy to draw a line and write the equation for. We're going to call it good there. We're going to go through a fun lab, hopefully, with writing linear models from data, finding a line of best fit, and extrapolating it tomorrow in class. Good night.